Okay, I'm full screen, very good. I'm on 2 monitors here, so let's hope that works well. But I can make changes if and when I find mistakes on my slides. First of all, I very much appreciate the opportunity to speak and want to thank the organizers for inviting me. It's also both good and a little daunting to come after Neil's talk. He did a great job explaining everything. He also covered some of the things I wanted to cover, but I'm staying lower level, and I guess I'll do things in more depth. So anyway, feel free to stop me with questions and so on. And so my talk outline is here. I'm going to talk about TFNP very briefly, and then which Neil's already introduced for us. And then I'm going to talk about resolution and PLS, and then the wrong proof problem, and then basically res, polylog, and CPLS. And some of the results are folklore. Some of them seem to be new, but we'll see. Maybe they're also known as well. We'll just see as we go along. And some of them are joint with Noah and Russell. Russell, I believe, is online with us, and Noah as well. Okay. So first of all, let me talk about TFNP. This was first introduced in a couple papers by Christos and Megiddo Papadimitriou in 1991 was the first version. So it's already defined in Neil's talk, but let me say it again. It's a total NP search problem. It's given by a polynomial time relation R. R takes 2 inputs, X and Y, and it defines the graph of a total multi-valued function, as it were. Namely, for every X, there is a Y such that R of XY holds. And Y can always be picked polynomially bounded with its length polynomially bounded in the length of X. And the TFNP problem is given input X, find some Y such that R of XY holds. And this is intermediate between polynomial time and non-deterministic polynomial time, okay, good. So I also want to talk about PLS, and this was defined even earlier. So a polynomial local search problem, I've simplified it down a little bit to get rid of the cost function. We have a neighborhood function n, a feasibility predicate f, and an initial value I. And the input is x here, and the neighbor nxs is supposed to give a value s prime such that s prime is the neighbor of s. F of xs means that s is a feasible solution for x, and I of x gives us an initial feasible solution. So we have the conditions that for every x, f holds for x ix, and for every x, if f xs holds, then f of x in the neighborhood of xs holds. And a solution is a point s where which is feasible, satisfies f of xs, and n of xs is greater than or equal to s. Clearly this is in TFNP because either the neighborhood function continues to decrease the value of s, or we can't do that forever. And once it doesn't strictly decrease, then we've got a solution. Okay. So a lot of times it's more convenient or more general to work with the Oracle versions of TFNP classes. This is sort of a black box versus white box approach. And Neil already mentioned that we have an exponentially large input, which can be either given in the white box method by a circuit that defines the input, or the black box method, which is an oracle, which gives us the bits of the input. And then we just rephrase the TFNP search problem to let the relation R have oracle access to the oracle omega. And other than that, the problem is exactly the same. So checking these size bounds at the bottom of the screen here, we can assume in the oracle setting that the input x is just a size parameter, that it's just a string of ones giving the size n, because any values we want to store can just be stored in the oracle instead. The size of the oracle, I'll tend to use capital N, which is 2 to the n to the O of 1, because queries to the oracle omega of z have the length of the query is n to the O of 1, because we're allowing polynomial time operations, and their polynomial time in the input x, or the length, their polynomial time in the length of the input x, thus an n. And we can likewise have an oracleized version of PLS. In this case, the feasibility predicates and the neighborhood function can access the oracle. Okay. So also, where I was coming at with this talk is trying to understand the connection between TFNP and the sort of modern approach where people are using CNF search problems. There's sort of canonical touchstone problem. So a CNF formula is a conjunctive normal form formula. A width n means that the clauses all have, width w means the clauses all have width w, where w is a function of the size of the CNF. The CNF search problem is the problem of given an unsatisfiable CNF formula and a truth assignment tau, find a clause that's falsified by tau. Just because the CNF is unsatisfiable, there must be some clause that's not satisfied by tau, and we choose it. And the observation here is that a CNF search problem for at least a sufficiently uniform family of unsatisfiable, exponentially large, polylog-width CNF formulas is the same thing as an oracle TFNP problem, right? So this is a sort of an elementary comment, but the proof is here, actually on 2 slides, in fact. A CNF search problem, okay, here's the statement again at the top. So to convert a CNF search problem to a TFNP problem, we assume we're given a sufficiently uniform family of exponentially large, unsatisfiable polylog-width CNFs and a truth assignment. They're all encoded into an oracle tau, and the TFNP problem is to find a falsified clause, or possibly to find a place where the CNF is incorrectly encoded by omega. As always, a solution to a TFNP problem must be verifiable in polynomial time, but given that the clause width is polylog, that means the same as little n to the O of 1, this is possible to do. If you're pointing to the clause, you can just look up the variables values, and if they're all false, then you know it's false. In the white box version of this problem, uniformly, the uniformity of the CFNP problem would mean there should be a circuit or a function that computes the bits in the exponentially large instance of the TFNP problem, or the exponentially large instance of the CNF search problem. In the black box version, we have more flexibility. You can just encode it into the oracle, and then all that's required is if there's a mistake in the encoding that you can detect that with a small witness. But it is important, some sort of uniformity is important, because TFNP problems have to always have a solution. That's the T total part of the problem. So you can't just throw an arbitrary CNF at it and say, find the falsified clause, because it might be satisfiable, right? So we need to make sure that you have something that ensures the clauses are unsatisfiable. And the reverse direction is maybe just as easy and maybe a little less obvious, is if you have a TFNP problem, you can encode it as a polylog-width CNF formula satisfiable search problem by just taking the, we're looking for the following. We're saying that I use this bracket notation here to say bracket R X Y omega is a propositional formula. It uses in the variables P sub z, which are intended to be the answers to queries to the oracle omega of z. And we say, we take the statement that R X Y omega accepts is definable by a decision tree of depth. First typo here. Little n to the O of 1. Not capital N to the O of 1. And hence it can be written as either a DNF or CNF of clauses or terms of size n to the O of 1. So we can write this whole statement that there is no solution to the TFNP problem as a big conjunction of log-width clauses. And so that's unsatisfiable because the TFNP problem is supposed to be total. So if you could solve the search problem, you could find a place where there is a solution. Okay. Okay. So do feel free to stop me with questions here. So that's the first observation then, as a CNF search problem. The second thing then is, and Neil already alluded to this, is a family of polylog-width CNF search problems as in PLS, if and only if it has uniform polylog-width resolution refutations. And this is really directly, there's no real, it's not a many-one reduction I'll talk about in a moment. It's really directly, you can take a CNF search problem with polylog-width resolution refutations and express it as a PLS problem and vice versa. So the forward direct, or the reverse direction is we start with a CNF search problem with a polylog-width refutation R. We convert it into a PLS problem by letting the nodes of the PLS problem be the clauses in the refutation. We'll say that a vertex S is feasible if it's falsified by the input truth assignment, which is encoded in omega. And that's checkable because in polynomial time, because the clauses are polylog-width. And the neighborhood function maps the, if you have an internal clause of the resolution refutation that's false, one of the two hypothesis clauses must be false, and the neighborhood function goes to that clause. And that can be determined which one is false just by querying the resolution variable, which again, if it's polylog-width, you can actually check which one is the resolution variable. And solutions are falsified input clauses. So that's the one direction, which is very simple. And the other direction is maybe a little harder to say, but similar in spirit. So suppose we're given a PLS problem that solves a CNF search problem, right? So the main conditions for the PLS problem can be written as three conditions. That the feasibility predicate F holds for X, the initial point I of X relative to omega, F of X S omega, if S is feasible for X, F X S omega holds, and S prime is the neighbor of S as given by the function N. If S prime is less than S, then S prime is also feasible for X, F of X, S prime omega. And if S prime is greater than or equal to S, then we're at a solution to the PLS problem. And the solution is supposed to give us a falsified clause. So we just let C sub S prime be the falsified clause that's given to us by the solution. And then all these things, F and N, are computed by polynomial-time oracle machines. And the oracle queries are what? They're the values to the variables P sub Z. If you query omega of Z, it gives you the value of a variable P sub Z that's a variable in the CNF search problem. So then you put these facts together to get a resolution refutation. So the negation Fx S omega is the conjunction of polylog-width clauses, just because it's a decision tree of polylog-width, of polylog depth, that is n to the O1 depth, little n to the O1 depth. And likewise, computing S prime from S is computed by a polylog depth, that is n to the O1 depth decision tree. It has L many possible values for S prime. I call them S1 through SL. Some of those correspond to clauses C sub Si. Some of them correspond to other non-leaf nodes. And if we have the assertions that the clauses are true and the other ones are not feasible, then a straightforward resolution derivation gives us that not Fxs omega holds. So that's actually rather straightforward. All of these things are sets. Well, the square brackets, not F things, are all sets of clauses of size n to the O of 1. And so you can put this together and get directly in a resolution refutation or a resolution derivation of not Fxs from the clauses displayed here. And so when you do this for all S and combine them together by the well-foundedness of the PLS problem's neighborhood function, we end up with a polylog-width resolution refutation of the initial clauses CS. Right. So we get directly a resolution refutation from the PLS problem. Okay. So very good. And this has a reflection of what's already known in bounded arithmetic. And Neil's already explained this, so I'll say it again here. We're working with either the theory T12, which Neil talked about, or the conservative theory S22, which is very closely related to it. These are the theories of bounded arithmetic. The T12 has induction on all NP predicates, on all sigma P2 predicates, sigma P1 predicates. And S22 has length induction, so-called P induction, on sigma P2 predicates, on NP to the NP predicates. And S22 is conservative over T12. And from results of Krychek and mine, and also Krychek, the provably total functions of T12 are the same as S22 and are the functions many one reducible to PLS. And Neil already mentioned many one reducibility, and what it means, just to say very loosely, is if you have a method of solving PLS, you can compute any provably total function of T12 by calling a single instance of PLS. The second point is then that the true for all pi b1 statements, this is the true universal statements for all co-NP statements of T12 and likewise S22, have straightforward propositional translations which have polylog-width resolution refutations. And this is from the so-called Paris-Wilkie translation, where you translate bounded arithmetic to propositional logic. And it takes a couple steps to make that go through, but you can end up going, you take a bounded arithmetic proof, you hit it with cut elimination, you change quantifiers into big ands and big ors, you play around with things a little bit, and you end up with this result, okay? And all this holds also if you have oracles in the language. That would be, you'd add second order objects as oracles. Okay. Am I missing a chat? No, I'm not missing a chat. Let me know if there's any questions. So now I want to switch gears a little bit and talk about the so-called wrong proof method or proof consistency search method, which also Neil talked about. So this comes out of, well, there was work of Jan Krychek on implicit proofs. Arnold and I worked on this, and also Goldberg and Papadimitriou worked on it. Arnold and I called it the proof consistency search method, and Goldberg and Papadimitriou called it the wrong proof method. They clearly have a much better name than we did. So I'm gonna call it that name, the wrong proof search problem. But basically what the wrong proof search problem is, you let T be a proof system, for instance, Frege or resolution, then an instance of the wrong proof problem for the proof system T is a purported proof in the theory T of a contradiction of, say, false. Again, an exponentially long purported proof. A solution to the wrong proof problem is the identification of a syntactic error in the T proof. And if we're dealing with proof systems which are just deemed to be consistent, so you can't prove a contradiction without making error in the proof someplace. So there must exist an error. And by a little bit of care, you can code up proofs so that any error, any syntactic error is easily detected. And Arnold and I looked at, and Jan also looked at wrong proof for Frege and extended Frege. Jan looked at extended Frege. Goldberg and Papadimitriou were looking at, they were trying to do a very strong proof system to go high up into the TFNP hierarchy. And they used a version of quantified Boolean formula reasoning with an ability to introduce Boolean functions with extension. They call it QEFF or QBF plus extended Frege functions. This talk, I want to go the other way and talk about wrong proof for weaker systems, particular for log-width resolution, constant width resolution, and also then resolution and res-log, which I'll define in a little bit. Okay. So the first comment is that PLS is many one equivalent to the wrong proof problem for polylog-width resolution. And this is almost exactly by the previous proof that I gave already, right? So I showed that something has a poly-width resolution refutation if only if it's solved by a PLS problem. And if you do that construction, you get the equivalence between, so the wrong proof problem for polylog-width resolution is many one, it's in PLS and it's many one complete for PLS. Okay, good. Feel like I'm going pretty fast, so questions are certainly welcomed.
Can I ask something?
Yes.
Yes. So in this case, what is wrong proof for resolution, in the sense that you can't derive 1 equals 0? So what is your inconsistency that you're deriving?
Let's go ahead a little bit here. Where's my slide for that? I have it someplace. Hold on, I have a slide about that. Someplace. I lost it. I'm losing my slide. Hold on. Oh, here it is. Here it is.
Okay.
I think I went too far. So a wrong proof resolution refutations as a TFNP problem. Thank you for the question. So an exponentially large instance is encoded by omega. Omega describes the following. There's a truth assignment tau. And for each clause, there's some knowledge of the presence or absence of each literal. So you have to, in polynomial time, given a index of literal, determine whether or not it's present in a clause. And if it's limited with resolution, we also need to be able to figure out the identity of all the literals in the clause. So if it's polylog-width, we need to be able to find them all out, right? Some clauses are initial clauses. If it's a large width clauses, then there's a function that gives us the literal that's supposed to be true under the assignment tau. If it's polylog-width, we don't need that function because we can just check all the literals to see if they're true. All other clauses are listed with two things. One is their resolution literal or variable, and pointers to the two clauses they're inferred from by resolution. And then the final clause is supposed to be the empty clause, and a solution then is either a falsified input clause or an error in an inference, right? And if there is these things about the pointers between being able to tell whether little's present and what you're resolving on and what you're being inferred from, all those things are enough to tell you, to let you see if there's a mistake in the proof. So that's important that we have enough information there to tell that. And of course, if you really wanted to get in some sense, we could dispense with a truth assignment and just insert a bunch of constants true and false for each variable, but that seems a little silly even. So I'm keeping it this way. That seems so counterintuitive. I'm keeping it this way, right?
Okay, so it's not that it's a proof of an inconsistency and there must be an error. It's more like a reflection where there could just be a false input clause.
Yeah, so it's possible that wrong proof should be better stated as a reflection principle, because for many of these systems, reflection is equivalent to consistency, right? But yeah, you have to be careful there. I'm not sure what the right answer is to that observation. Okay, let me figure out where I was in the talk.
Sorry, let me ask a quick follow-up. Do you mind if I ask a quick follow-up to that? I mean, these are very similar to like these ref tautologies in this non-automatability proof, aren't they?
The graph tautologies.
The ref tautologies.
Oh, ref. Oh, yeah. By Atsarius and
yeah, yeah.
Good
like
question.
Basically the same thing, it seems.
Right. Okay. I hadn't thought of that connection, but I think you're right. That's a recent result. It was just a year or two ago. So yeah. But yes, it does seem very similar to that.
Isn't it just the search problem for reflection, negation of the reflection principle for resolution?
Yes, I guess it probably is. Okay. Yeah. I hadn't made that connection, but yes, I think it is. Okay. So then, okay, good. So then we already showed this theorem. Did I skip that slide there? I somehow missed that. I think I jumped over that slide somehow. Okay, so PLS is many one equivalent. And then the other comment is that in fact, the wrong proof problem for width 3 resolution is many one complete to the wrong proof problem for polylog-width resolution. And this is a fairly elementary proof. we just have to say the following, that if we have a polylog-width resolution refutation, we want to convert it to a width 3 resolution refutation. And the idea is we introduce new extension variables for all possible disjunctions of n to the O of 1 many literals. There's exponentially many of them, but we have an exponentially big proof space available, so we can just do that. And then we introduce all these variables by extension, which can be done with width 3 clauses, and then we can reduce the width, the polylog or the width n to the O of 1 clauses to width 3. And this relates almost immediately to effective quasi-P simulation. So this is the notion of P simulation is an old idea that goes back in at least some form or other back to Reckau's thesis on comparing proof systems in different languages. But the sort of the modern version of it, you can see a proof in Tony's paper with Rahul from, I was going to say recently, but it's been 12 years ago. I've got the date right. So proof system P strongly, effectively P simulates a proof system Q if there's a truth-preserving transformation F, computable in polynomial time, which takes any formula phi in the proof system for P and transforms it to a formula F of phi in the language of Q, such that any Q proof of F of phi can be converted back to a P proof of phi in polynomial time. Okay, and we can also define effectively quasi-P simulates the same way, just replacing polynomial time with quasi-polynomial time, right? And then so the previous proof method I just gave on the last slide shows also that width 3 resolution strongly effectively quasi-P simulates log width resolution by just almost exactly the same proof. So, which is an interesting observation as well, how this connects back to TFNP. Okay. Oh, and small note here, I've slightly changed the definition here, but it doesn't change anything important, right? Okay. So now I want to switch to res polylog. So a T conjunction means a conjunction of at most T literals, and res f of s means a resolution extended to not having clauses over literals, but having clauses over small conjunctions. So res fs means the lines in the refutation system are disjunctions of conjunctions of size f of s, measured as a function of the size of the overall refutation. So we'll talk about res 1, which is the usual resolution, and res polylog, which in our setting means res n to the O of 1, because our proofs are exponentially big. Okay, so now we step back to bounded arithmetic again for a second here. T22, this is the next level up from T12, and has a conservative extension S32. And these are the theories. T22 has induction on, has full induction on sigma P2 predicates. That's the NP to the NP predicates, and length induction on sigma P3 predicates, which is the next level of the polynomial time hierarchy, NP to the NP to the NP. And as Neil mentioned already, the provably total functions of these theories are the functions that are many-one reducible to CPLS. And I will give you the definition of that in a moment. And the Paris-Wilkie translations for these theories give us that the universal consequences of these theories have straightforward propositional translations, which have res polylog refutations. And these holds also in the black box setting where you add oracles. So we expect now the same kind of connection between CPLS and res polylog as we had earlier for res and log width res. And indeed we get that, but first let me define CPLS. So it's defined similarly to PLS. We have a new predicate, I call it capital C of X, S, Y, to say the node S has color Y. And lowercase c of XS gives a color to the terminal node. That's the input nodes, right? And a CPLS problem has the neighborhood function, the initial function, the little color function, and the predicates capital F and capital C. So that we have that the first principle is that for every input X and every color Y, the initial vertex I of X is feasible and it has no color, right? And we're going to think of this like corresponding to the root of a refutation. And then the neighborhood function, that's the second point, takes feasible points to feasible points. And the third principle says that if the neighborhood function goes from a node S to a node S prime, and if the node S prime has color Y, then the node S has color Y. So the neighborhood function, so colors propagate from the neighbors back to the point that it's a neighbor of. And then I'm stating it this way just to make the next theorem flow a little better. A solution to the CPLS problem is where it fails that one of the leaf nodes has the designated color. So for all X, if S and S also, if S is feasible, and I should probably put some S's in there. S and S and S, maybe some other variables Y as well. Y, I'll update my slides with some variables here. If f of X, S holds, and the neighbor is S is greater than or equal to S, then the little c function gives us a color that holds there. And then we can relativize this, of course, with an oracle, just the same way we did PLS. Okay, so that's the definition of CPLS. And so the first thing here is that we have exactly the same theorem as before, pretty obvious. A family of CNF search problems is in CPLS if it has sufficiently uniform resolution refutations. And Neil and I probably need to talk about this offline. Neil said this for res log, but I think it's maybe more correct for res, but we'll get to that on the next slide. The proof is a little more difficult than before because we need to now take the clauses in the resolution refutation to be the disjunction of the possible colors of a node. So the capital C predicate can tell us whether it's possible that Y, the color Y, is there, but of course you have multiple queries. Okay, and then so it's then equivalent by the same proof. The CPLS search problem is many one equivalent to the wrong search problem for resolution, and then we also have, again, by this method of extension variables, the wrong proof search problem for res 1 is many one equivalent to the wrong proof search problem for res polylog. And again, by the idea of introducing extension variables for all n to the O of 1 many possible conjunctions of literals. And this then feeds back to strongly effectively quasi-P simulates as well. Resolution strongly effectively quasi-P simulates res polylog. And here, I think, if you look at Tony's and Rahul's paper, and they build on some earlier work of Albert and Maria Luisa, that they prove this theorem for K, constants K instead of polylog, but I think it's exactly the same proof, right? So that gives us an equivalence here for that as well. So this is what's going on, I think, trying to bring together different ideas between wrong proof, between TFNP, between CNF search, and between different flavors of resolution, and more generally bounded depth Frege proofs. So I was going to finish up with some just concluding comments here. I hope I'm not yet out of time. First comment is, although I gave you two theorems where strongly effective quasi-P simulation or equivalence is the same as equivalence of the wrong proof search problems, this isn't always the case that we have this equivalence. So in particular, there is a maximal proof system, a quantified propositional logic, G sub 0 as it was called, that's the strongest possible proof system for effective P simulation. And it's a kind of quantified propositional logic, and they use a reflection principle for the proof and so on. But this doesn't seem to work to give a strongest possible proof system for wrong proof search problems. And the reason being that the way the quantifiers work in their reflection method. The second comment was if you take the wrong proof search problem for Frege proofs, this, and I guess Neil alluded to this as well, this includes all the provably total functions of, or it's any-one complete for all the provably total functions of U12. This is the theory for polynomial space computations. It doesn't mean polynomial space that produces exponentially big output. It means polynomial space computations that produce a polynomial size output satisfying an NP property. And this includes all the usual quote unquote TFNP problems. I think it includes everyone that Neil mentioned in his talk, but includes PPA, PPAD, pigeonhole, PLS, etc. But what can you say about stronger classes for extended Frege, which corresponds to V12 or Q sub F, Q sub EFF from Goldberg and Papadimitriou, or one could certainly envision stronger propositional proof systems beyond that. And is there some natural stopping point up there where it doesn't make sense to get stronger, or does more and more interesting stuff happen as you get stronger? The third bullet point is partially answered by Neil in his talk. I hope he doesn't mind my asking this question, but it seems to me we have CPLS as a really beautiful theory for T22, and there's various things above that, like the game induction principles, and I guess Li sub k, the local improvement principles, can be put up there. And then are there other better ways to do things in higher levels of bound arithmetic carefully? And finally, what about wrong proof search for other weak propositional proof systems, cutting planes, SOS? For instance, it's not too hard to get something for Nullstellensatz already. We've been talking about that, but that seems to be sort of other general directions here. So I think I'm about out of time, so thank you.
Thank you. Thank you both. It was a really great session. Really enjoyed it. Does anybody, we have some time for questions. Does anybody have any questions?
Can I ask a question? So how do you encode these resolution proofs in your circuit? I mean, depending on how you code it, I mean, the TFNP class can change. I mean, you can, like, for example, if you add something like a diff of the clause for each clause in the proof.
So a diff, you said?
Yeah, some rank that where this clause appears in the proof, then you can do something like maybe, I don't know, PLS or polynomial-time. I mean, or if you like permute the proofs too much without any like rank. I mean, because the proof is a graph and you are going to represent the graph as a circuit, and
right. Okay, good point. So it's implicit here is that I should have probably mentioned this, is the proof is in order. So we assume the clauses are coded in omega in the order they appear in the refutation, so that there's no question of how do you know it's a DAG. So we know explicitly that whatever's there is a DAG just because clauses are inferred from earlier clauses, right? Okay. So I mean, it could be a DAG with exponentially long paths, so you can't follow them, right? Maybe that's part of the answer to your question. I'm not sure I got the rest of it though.
Yeah. Okay. I get it. Yeah, that answered. Thank you.
Okay, good.
I have a question. So it seems in general that most of these reductions between different classes are, many one. Are any of these examples Turing? And what's seems strange to me. Oh,
yeah. There are. Okay, I actually don't have this at my fingertips. If you look at, I had a student, Alan Johnson, who worked on some of these things. Who we did have some problems there that were only Turing reductions, but I couldn't tell you which ones they were now. But we definitely had some problems where only Turing reductions were known, and
that would be interesting.
Not many one reductions. But yeah, no, you're right. That's also a very good question. And in bounded arithmetic, it probably would be fine to have a Turing reduction between PLS problems, right?
Yeah,
So
or
you can
what's-
always do this a little bit, you know, for instance, you could always do this in an ad hoc way by take the some sort of disjoint union of two search problems or something like that. And so if you take, you know, the disjoint union of PPP and PPAD, then it's, you know, not, you know, so I would say, what should I say about that? Is that, well, you could take the, well, you take something where you take the cross product of PPA and PPAD and the disjoint, well, actually, let's do PPP and PPAD, take the cross product of that and the disjoint union. Then you have two calls to the disjoint union will let you solve the cross product, right? But that's an ad hoc, rather artificial way to do it. We had some more natural examples of that, but I couldn't quote them right this moment.
Great, okay.
I can just say something about it. In my talk, I defined the TFNP things provable in a theory. And if you had this right base theory, then it was closed under many one reductions. But if you have a slightly stronger base theory, including S12, then you get closure under Turing reductions.
Right.
And really for the bounded arithmetic stuff, these two theories are kind of the same. So the things for
Okay.
many one reductions will also work for Turing reductions.
I see.
Sam, what problems might occur if you try to do the wrong proof thing with the extended Frege?
So nothing, okay, so nothing goes wrong at all. You have to be careful to set it up so you can check. You can't just literally write out the proof as a string of symbols. We need to have pointers, not only with what formula is inferred from what other formulas, but also what parentheses are matched with which parentheses. So you need that kind of information just to parse formulas. And then what goes wrong? Nothing goes wrong with the wrong proofs for extended Frege. The theorem is that the wrong proof problem for extended Frege is many one complete for the consequences of the theory V12. And V12 is the theory of exponential time. So it'd be the exponential time computable functions that yield answers that are NP checkable of polynomial size. Okay.
Okay, I see. Very interesting. Thank you.
Yeah. So my thought is the Goldberg-Papadimitriou class QEFF must belong to some much stronger theory that no one's ever really looked at before. If there is, there probably is a theory up there someplace.
Okay, if there's no other questions, I'll just thank the speakers one more time for a great session, and stay tuned tomorrow for we have some part 3 of this about propositional TFNP by Robert, and following that is an interesting talk by Jan Krajcek on what tautologies know about their proofs. So information theoretic view of proof complexity. So hopefully we'll see you all tomorrow.
Thank you.
See you.